Right, hello, this is section 2.2 for Calc AB, and we're going to be starting our discussion on basic differentiation rules. And the nice thing is you've learned how to find derivatives, but the only way you've learned so far is using the definition of derivative. And today we're going to get introduced to some actual shortcuts that save you a lot of time and headache. So the first one, and you may have logically thought through some of these, you just didn't realize it. So the first one, the constant rule. So if, remember this notation, d dx means you're going to do the derivative of what the function that follows. So the function is just a number, meaning it's a horizontal line. Well, if it's a horizontal line, what's the slope of a horizontal line? It's 0. Okay, so anytime you do the derivative of a number, it's just 0. So, and that's what this demonstrates here. So we have two functions that are equal to numbers, and notice these numbers can kind of look complicated, but that's just a number, and therefore the derivative is 0. Same thing with 3/7. Now, let me side note, there are proofs for these in your book, and in class we will discuss these proofs, but for these videos, to make them shorter, we'll just go over the rules. Now the next big one is the power rule. This one will save you lots of time. So if you have x to the n, where n is a rational number, remember the d dx, you're going to do the derivative of this, then all you have to do is pull that n down in front and subtract 1 from the exponent. Oh, cool. And that's the derivative. So I'm going to pull this up. This was the notes we did for 2.1. And here's where we use the limit process or the definition of derivative. And notice we went through all these steps, but if you use the power rule, so if you pull the 2 down in front, now you have to multiply it by this number. So 2 times 4 is 8, and subtract 1, this derivative is 8x. Oh, and it works with this as well. This is raised to the first power. So if you pull the 1 down and multiply, and then when you subtract 1, 1 minus 1 is 0. So x to the 0 power is 1. So it's actually just -5. So that's much faster than going through this big process here. Okay, but it works. All right, so I did some of these problems. So x cubed is a very basic one. You pull the 3 down, subtract 1 from the exponent. Now, in this case, the power rule is not in the denominator. So you've got to move that x squared up. Make it to the -2, then you can use the power rule. So pull your -2 down in front, subtract 1, be careful with the negative exponents. Now, x is raised to the first power, so we can actually use the power rule. Pull the 1 down in front, and when you subtract 1 from the exponent, x to the 0 is 1, so it's just 1. So you might realize, hey, when I have a linear function, it's actually just the slope, which I hope makes sense, because if you have a line, the slope of the tangent line is going to be 1 and the same. Therefore, the derivative is the slope. And I'm going to come back to that 2.1 notes and show you. I'm going to scroll up here. We saw that happen with this problem. So we were given this linear function, and we went to do the derivative. I asked at a specific number, but it doesn't matter. Since it's a line, the derivative is always going to be -5. Okay. All right, so, and then if ever there's a radical, rewrite it so that the exponent's a rational number, and then just use your power rule. Pull the 2/3 down in front, subtract 1 from your exponent. Okay. Now, in this case, find an equation of the tangent line to the graph. These problems will pop up a lot. So you're going to need to do the derivative to find the slope of the tangent line. That's what the derivative gives us. So first rewrite this so it's x to the 1/3. I didn't write that down, but make that x to the 1/3. Then pull the 1/3 down in front. That's what's happening here. And subtract 1 from the exponent. That's the derivative. And I want to plug 1 into that derivative, and that's what's giving me 1/3. That's the slope of the tangent line when x equals 1. But I'm not done. Now I need to write the equation. So then you'll want to plug 1 into your original function to get the ordered pair, and that's what this is. So now I have a point and I have a slope. So y minus 1 equals 1/3 times x minus 1. So the slope of the tangent line comes from the derivative. The ordered pair comes from the original function. Now we've kind of already seen this happen. When you have a constant multiple or a scalar here in front, then it just stays out in front and you do the derivative of what follows. That happened. Let me pull this back up. That happened here where we had, sorry, a little bit further down. When we had this 4x squared, we pulled the 2 down and we multiplied by that scalar 4, and that's what gave us the 8x. Okay. And that's the same with limits as well. And you have to be careful though. Not all of the properties that work with limits will work with derivatives, but in this case, the scalar does. So here are some fun examples with scalars. You'll notice the first one's very straightforward. And I want to point out, you can write dy dx, or you could write y prime there. Either way is fine. Now, in this case, this is a frequently missed problem. You cannot use the power rule because x squared is in the denominator. So you've got to move that x squared up. But for some reason, students like to move the 2 up as well. No, leave the 2 where it is. It's not hurting anything. And if you move the 2 up, you have to write it as 2 to the negative 1. So why would you do that? So leave it as 3/2 and then just move the x squared up. So x to the negative 2. Then you can do the power rule. So pull the exponent down in front and multiply and subtract 1. Make sure you're labeling. Notice I had to do a little manipulation before I could do the derivative. Students will do this manipulation and think, oh, I did some work. I must have done the problem, and move on. And they'll leave me this as the answer. You didn't do any calculus. You didn't do the derivative. So make sure you're labeling so you know when you've actually done the actual problem. That happens a lot, actually. Okay, now in this one, same idea. Leave that 2 in the denominator, but move up that x to the 2/3 and make it x to the negative 2/3. Then you can do the power rule. Now in this case, you'll need to notice it's not just x to the 4th. You can't use the power rule. The power rule only works when it's x to the n, and that's not the case here. You have 3x to the 4th power. So multiply it out. 3 to the 4th is 81, and then x to the 4th. Now it's just a scalar times x to the 4th, and then you can use the power rule. Same idea here. Rewrite it first. So square that 7x. That's giving me the 49, and then I move the x squared up, and then I did the power rule. Okay, that will come with practice. Then you have to do the homework to learn those lessons. I can show them to you, but you have to learn those on your own. These are the perfect problems for you to work out and then check your answer to see if you're getting the same thing. When you're not, learn from your mistakes. And if you can't figure out your mistakes, that's when you ask me. Okay, so if you have the sum and difference, so if you have 2 different parts, 2 different terms, or more than 2 terms, then you just do the derivative of each term. You treat them like 2 separate derivatives. Okay. Same with subtraction. So in this case, that opens us up to these nice, more complicated functions. So you just literally treat each part as its own separate derivative. So, and you can use the power rule. And then down here at the end, -5, that derivative is just 0. Now in this case, rewrite that radical as a rational exponent, and then just do the derivative. There it is. Now, I'm going to say this so many times this year. If ever there is a monomial in the denominator, chances are it's going to make your life a lot easier if you distribute it to the terms in the numerator. There it is. And look how much easier that derivative is. And you don't know how to do derivatives with fractions yet, so you kind of don't have a choice. You need to distribute it. But that is coming. You'll get to learn that later. And then look at that beauty. You get to practice with some of your fractions. All right, so these would be good ones for you to do on your own to see if you're getting the same answer as I am. Okay, and the AP, you don't get any extra points for simplifying. So with a lot of these derivatives, you're going to leave them in this form. All right, don't worry about factoring yet. Okay, so here's some more fun new rules. So sine and cosine, and here's a nice little proof down here for sine. And you'll notice I use the your definition of derivative, use the limit process and all that. So a fun one to look through. And it uses an angle addition property where you can break it up, and then you can combine and use your special trig limit. So it's actually a really cool proof. Okay, but anyways, sine, the derivative of sine is cosine, and the derivative of cosine is negative sine. Now this actually creates a loop. So over here, sine, cos, minus sine, minus cos, and then it loops back around. So I sing that little jingle, sine, cos, minus sine, minus cos, sine, cos, minus sine, minus cos. So the derivative of negative sine is negative cosine, and then derivative of negative cosine loops back around and is sine. So if that helps you, great. If not, you don't have to use that. And then here's the easiest derivative, and there's a lot of really funny math t-shirts that joke around about this, but the derivative of e to the x is e to the x, and you're done. So it's exactly the same. So that's a cool derivative. All right, so here's some more practice problems down here with these new rules. So I'm just going to look to see if there's any that I want to point out that are interesting. With this cosine of x over 2, realize that that's technically 1/2 times cosine. That's a scalar. And then here's one of those classic that looks like a complicated derivative, but it's really just a number. So the derivative of cosine of pi over 2 is 0. So watch out for that. All right, and then here's some e to the x's. So if ever there's a scalar, just leave it in front, and the derivative of e to the x is e to the x. So, okay. All right, and then this last big concept, rates of change. So S of t is referred to as the position function, and here's the formula right here. You guys do this in physics. Negative 32 is your acceleration in terms of feet per second squared. Negative 9.8 is your gravity, I should say, acceleration due to gravity when it's meters per second squared. Usually we give you that. That's not something we would, I mean, it is, if you do enough physics, it's kind of common knowledge, but we'll probably give you those values. So G is your gravity, depending on if you're in feet per second or meters per second. And then V initial, that's your initial velocity. And then S initial, that's your initial height that you're starting at. So notice, here's what's new. S prime of t, the derivative, is the limit as the change in t approaches 0 of your change in distance over change in time. That's just your derivative. Remember, without the limit notation, it's just the slope. But as soon as you add this in, now you're getting the instantaneous rate of change. So the derivative gives us the instantaneous rate of change, and then the double derivative gives us the acceleration. Okay. So here's a couple examples with, oh, sorry, I scrolled up too much. Tennis balls dropped from a height of 150 feet. The ball's height s at t, time t is the position, and they're giving us the position function where s is measured in feet, t in seconds. There's a little typo there. Find the average velocity over each of the following intervals. So we're just using this position function, and we're basically doing the slope. And you can see, notice 2 to 3, 2 to 2.5, 2 to 2.1. We're moving, we have a point at 2, and we're getting closer and closer to it. So you can see what the slopes are doing. So what is happening as the intervals narrow? Okay, we're getting a better approximation of what that slope of the tangent line is, and we can easily see that this is a function that is decreasing pretty fast. All right, so then here, now let's actually use our derivative skills we've been practicing. So a water balloon is thrown upward from the top of an 80-foot building with an initial velocity of 64 feet per second. Height in feet of the balloon can be modeled by the position, where t is the time in seconds since it was thrown. All right, so how is the water balloon in the air? There's no calculus involved here. When does that water balloon hit the ground? Well, that's when your position function equals 0. If you can factor, solve it by hand, but you probably get a graphing calculator to help you with this one. But solve it for 0, set it equal to 0, and you end up with t equaling 5. Now, what is the velocity of the balloon when it hits the ground? Here's your calculus. I want that instantaneous rate of change when the balloon hits the ground, and you haven't been able to solve that yet. That's what you need calculus. So find the derivative. You can easily find that derivative and then plug 5 into the derivative. And now figure out how fast it's going when it hits the ground. And it's decreasing, obviously, it's falling. That's what that negative represents, 96 feet per second. So, okay. Please do your homework and practice these new derivatives and email me if you need any help.